looking at these structures again, we have just written out, instead of these bulky groups, the names or numbers for these groups on the orientation pattern. And I was showing you in the previous part of the video that we keep our number 4 at the back. Ignoring number 4, you will now observe in which direction your groups have priority. So this is number 1, and I'm going to now start from here to number 2, from number 2 to number 3. And what is the rotation that I am observing? Is this clockwise or is this anti-clockwise? Clockwise, and hence this carbon is labeled with the R configuration. So remembering this, we assign R or S. A fifth step that you need to know is, what if your number 4 is not at the back? Then we switch 2 sets to make number 4 at the back. What does this mean? It means that we copied down the exact orientation with all of the priority numbers on those bonds exactly where they are. And then we want to make our number 4 be at the back or the dashed bond. For example, in this case, when I made my first switch, I switched number 4 and number 2. But I kept my number 1 and number 3 where they were. As my second switch, I switched the positions of number 3 and number 1. Once you have made your first switch, your number 4 going at the back, the next you can make any switch. You can switch 2 and 1, you can switch 2 and 3, and you can switch 1 and 3 as I have switched. This will help you take your number 4 at the back and then figure it out again. What is the orientation of your bond types according to their priority? Always remember to keep the orientation as is. Do not move it around as your will. So if I have a molecule like this, I cannot draw it in a random manner. I have to make sure that the orientation stays the same. This is what I mean. So you keep the orientations same, and then you start to switch your atoms. And we see that 1 goes to 2, 2 goes to 3. And what is this rotation? This is an anti-clockwise rotation. So this carbon has the S enantiomer. Whenever you're trying to switch positions, always remember to switch twice, because the first switch that you make will create the enantiomer of the original compound. When you will make the second switch, you will create the enantiomer of this compound, which is the original compound. Let's do another example. Let's say that I have this particular structure and I have to assign R or S at the carbons. So what is the first thing that I'm going to make sure that I have? I'm going to make sure that I have the sp3 carbon to work on before I go ahead and start assigning my R and S. So I'm going to look at this carbon first. Is it my sp3 carbon or is it not? And I see that there are 4 groups around this carbon and it is a sp3 carbon. But are all the groups different? So while 2 types of the groups are definitely different, these 2 are not. So I know that this particular carbon is not chiral. Similarly, this carbon, it has all 3 hydrogens as exactly same compound, same groups. So this is also not a chiral carbon. Same with this. This carbon, however, has 4 electron densities around it and it has 4 different groups around it. How do I label them as R or S? First, I'm going to mark an asterisk just to make sure that this is the carbon of my interest or the chiral atom that I'm going to look at. I will then look at all my A atoms. And I observe that hydrogen is going to be the smallest and OH with the oxygen directly attached is going to be the number 1. Out of methyl and this bulky group, methyl is going to have lesser priority. This group would have more priority. So I can just go ahead and look at the next step. Number 4 should be at the back. And so this is what I see here. My number 4 is already at the back. But I can still redraw it. You do not have to redraw it right here, but I just want to show you how I'm going to draw my orientations around this chiral carbon. And I'm just going to write my priority numbers. I will hold down my number 4 or just ignore it. Go to 1, to 2, to 3, which is a clockwise kind of a motion. And so I will label this carbon as my R group. So looking at this particular molecule, let us first figure out if there are any chiral atoms. And we are only focusing on the carbon compounds. So what are the requirements that we need to have for an optically active carbon site? It needs to be sp3 hybridized. All of the groups on that sp3 hybridized carbon should be different and no symmetry should be present. So where on this structure are we going to find these chiral carbons? And we have to scan the molecule starting from one side. Let's start from the top portion. This carbon right here is definitely sp3 hybridized, but has 3 same hydrogen atoms on it. This carbon right here is sp2 hybridized, so we're not going to look much into it. This carbon right here is sp3 hybridized and has 4 electron densities, with each of the group as a different group. So just pay attention to this carbon right here, which I'm going to redraw. So there is this hydrogen also, a hidden hydrogen. And these are the atoms A, carbon carbon A. If I keep on going, on the B atom, on this hand, you have a nitrogen. But as an atom B, on this side, I have an atom C. So both of these are different groups. Nitrogen being more in atomic mass than carbon, this group would have more priority over this particular group. However, if you look at this carbon, which is also atom A on this side of the bonds, this is sp2 hybridized. What do we mean by a double bond? It means that carbon is attached to oxygen 2 times with 2 different bonds. The sigma and the pi are considered as 2 bonds, and hence this group where the atom B is oxygen and not one oxygen, there are 2 oxygens. And of course, this carbon right here is also the B atom. So on this carbon atom A, there are 2 oxygens and 1 carbon. On this atom A, I have 2 hydrogens and 1 nitrogen. On this atom A, I have 2 hydrogens and 1 carbon. So you can see who will have the most priority. This is going to be number 1, then number 2, number 3, and number 4. And if we were sure of what the orientations at this carbon site would be, we would know how to do the R and S. But for now, you should just focus on assigning the chiral atoms first. And hence, definitely, this carbon is a chiral site. What about this carbon? There are 2 same hydrogens on it. What about this carbon? There is a little hidden hydrogen here. If I start comparing this atom A for this carbon, which is of our interest, we see that HA and then Ca and then this Ca and then this Ca. So you have to keep walking away from the carbon of interest until you find everything as similar or some difference, even a single point of difference. So if you look at this particular carbon A, what does it has? It has 2 hydrogens and then 1 carbon atom. 2 hydrogens, 1 carbon. What about this? This carbon also has 2 hydrogens and 1 carbon. What about this carbon? This carbon has 1 hydrogen, 1 nitrogen, and 1 carbon. So these 2 groups are definitely different. And among all of these, we can label this as 4 and this as 1. So if you observe, this carbon is branched. Branching will definitely increase priority. Moving on, we now have to decide between these 2 carbons. So if you look at the atom B now, so we had looked at atom A's on these groups, we are now going to observe atoms B. This atom B right here has what on it? Don't look back, look in the front. Okay, so this carbon B was attached to carbon A. We are not going to look back. We are just going to look in the front. So atom B is attached to atom C. Atom C. There is of course a hydrogen here, which will act as your third atom from the carbon of your interest. So this particular atom B has one hydrogen and two carbons. This carbon and this carbon and this hydrogen. On the other hand, if we observe this particular carbon, we have atom C here, atom C here. Now don't get confused, this CB initially belonged to this atom, but we are not at this site anymore. We have to consider all of the atoms from the carbon of our interest, and for different carbons our labeling will change. Okay, so do not worry about that. So on this particular atom B, I have one carbon here and one carbon here. But I want you to remember this carbon and this carbon are double bonded. So there's a sigma bond and a pi bond. So I would not say this bond is attached to just one carbon. I would say it is attached to two carbons. And so if you compare this part of the group with this part of the group, at the third atom we see the difference. Two carbons can be cancelled out with each other. Who is left? This one carbon. So if I have to redraw this part again, and let me draw the hydrogen also, I will label this end as number 1, this end as number 2, and this end or this group as number 4, and this as my number 4. So around this particular carbon atom, all the 4 groups are different, and I have given them the priority also. So at this point, we know that there are 2 chiral atoms. What about this? Yes, this is also a chiral site. There is a hydrogen, there is a nitrogen, there is this bond type, this group also. And all of these groups within the ring can also be different. What about this carbon? This cannot be chiral because it is sp2 hybridized. It cannot be chiral because this is also sp2 hybridized. This is sp3 hybridized but with same groups on it. And hence, on this particular molecule, there are these 3 chiral sites, and it can have R and S enantiomers or configurations on it, depending on how many other molecules can be possible. So if a molecule has 3 chiral centers, how many stereoisomers are possible from that compound? We say 2 raised to the power n, where n is the number of chiral center in that molecule. So this particular molecule can have 8 stereoisomers possible because of the 3 chiral centers that we have figured out. So make sure that you know the sequence of R and S and how to assign priority, how to assign clockwise or anti-clockwise motion. If your number 4 is not at the back, what do you need to do for that case?